Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. Climate science is yet another application where machine learning is rapidly being adopted. In this episode, I interview Zach Labe about the use of layerwise relevance propagation as an explainable AI technique. It can be used to better understand how deep learning models are able to make predictions about the climate system.
My name is Zach Labe, and I'm a postdoctoral researcher at Colorado State University in the Department of Atmospheric Science.
Can you tell me a little bit about what you're working on in your postdoc?
Currently, I really classify myself as a climate scientist. I tend to think about climate change and climate variability, which I'm sure we'll talk about more. And my work really comes at climate change and thinking about it from the perspective of data science. I'm not only using, climate model simulations, which are these huge, big types of data sets, but also diving into machine learning. And for me, I've actually only been in this sort of machine learning AI world for only about a year now. I didn't really do it in my graduate school, but for my postdoc, I was really hoping to, learn a new skill set to really apply these types of tools to climate data to better understand climate change.
Well, despite being relatively new to it, certainly you'd been at least aware of or had heard of machine learning. Are there any takeaways being a year in? What was surprising or unexpected about it?
For the field of climate science in general, we have lots of tools really to extract patterns in climate change. That's really what we're all about, is looking at maps of data and looking at patterns. And we already have all of these existing tools. So I think going into machine learning, I was skeptical that the machine learning model, perhaps it could be better statistical, analysis, but is it really using physical, real mechanisms in the climate system? And I think I've been relieved and happily, surprised to see that at least the things I've worked with, the machine learning models, are really using like physical things that I know as a climate scientist exist in the world to solve these problems. So I think it really, to me at least, has added credibility to a lot of these methods for applying these to climate data problems.
Could that be due to researchers like yourself who have done a really good job of feature engineering? Or is it that machine learning is really figuring things out given the right data?
Yeah, I think it's a bit of both. I think one thing that's been important, at least in the work that I've done, to at least give me this idea that these models are doing credible physical processes, is this explainability methods to really try to understand what's going on in the black box. I think has been so important for me to really help, as I said, give credibility to the machine learning problem, but also, learn something new. It also sparks me new ideas for my research.
What are some of the questions that you can use machine learning to help answer?
I think the way I have looked at machine learning so far is actually a bit different than other approaches, where often machine learning, at least in weather and climate in the world I live in, is often used for prediction problems. Maybe we're trying to get a weather forecast or a climate prediction, and they set up these advanced machine learning statistical models to make a prediction. But the way I have approached it so far is actually setting up very simple machine learning problems where the answer necessarily is not interesting at all. However, using the explainability methods, that's where we can actually learn something new, and new being patterns. I can look at these features like a map of a climate variable and use the machine learning methods to understand patterns, which is what we're really interested in climate science.
And why is machine learning required? Why can't a couple of grad students find these patterns?
I think that's the hard question, and something I grapple with is, I often get asked, what is the advantage of using machine learning methods? Why not use traditional linear regression problems? I use artificial neural networks, so what is the advantage? And I'll say it's difficult to sometimes answer that. One answer being that we don't know if we don't try. We don't know if we can find interesting nonlinearities by using these types of, something like neural networks. But But other things, these explainability methods we're doing really give us maps of data, which is something climate scientists always work with. And it's really nice that we can compare multiple different types of methods, statistical toolboxes that we have, and see how these AI methods compare. And sometimes they may look exactly like other methods we may have used, like principal component analysis. But other times we might find new patterns. And I think that's what's so exciting about this field, combining data science and machine learning with climate science and other weather and geoscience applications, is that we really don't know what we all could find. And I think it's wide open for future research and new graduate PhD theses.
Well, the main paper I invited you on to discuss is titled Detecting Climate Signals Using Explainable AI with Single Forcing Large Ensembles. Could you elaborate on what the single forcing part is all about?
Sure. And I think the single forcing aspect is the unique part of this work. So just a little background from climate world is we often look at climate models. So climate models basically are running lots of different types of equations to try to simulate the climate of our planet, both in the past, but also the present and in the future. And these climate model simulations have all sorts of things interacting. They have changes in the ocean and in the atmosphere and the ice, and they all couple together. So there are these huge, simulations that require expensive supercomputers to run. And often when we run them, we include climate forcings. So what I mean by that is things like changes in greenhouse gases like carbon dioxide to understand how that affects the climate. But normally, when we run these simulations, we include all of the forcings. So all the things like changes in aerosols, like particles in the atmosphere that come from factories, things like carbon dioxide and other forcings, they all change at the same time. But what's difficult is really to understand the climate change aspect of it. Is, if we have a region that's warming up, over North America, how can we attribute that warming over North America to these different forcings, something like an aerosol or something like carbon dioxide, or perhaps something like changes in the land? So recently, they've run these new simulations. They're called single forcing simulations, where they take a climate model, and one of them will run it with all of the realistic forcings, just like the real world. Then they'll run another simulation that's completely identical, but in this case, they will actually hold carbon dioxide constant. So it will not increase while everything else is changing like the real world. And then they'll run another simulation where aerosols, the particles in the atmosphere, don't change, but carbon dioxide does. And the idea is by running these simulations where we kind of hold different forcings constant or let them evolve through time, we can try to pick apart and actually attribute how changes in the climate are caused by these different forcings.
And as the title suggests, it's doing these detections with single forcing large ensembles. What are the ensembling techniques and why were those called for instead of just some, linear regression like you suggested?
So for a climate model simulation, we can run one simulation and that will be a realization of the world with all of the changes in carbon dioxide. But we can also run that simulation again. And in that case, we get this idea that there's natural variability in the climate system. So basically, there's this unpredictable noise in the climate system that you could think of that as like changes in the weather. Tomorrow won't be the same as today. And that is a very unpredictable part of the climate. So a challenge for climate scientists is trying to understand, is the change due to something like carbon dioxide, or is it due to this sort of inherent unpredictable variability, this natural variability? So what we do when we run climate models is we run ensembles. So basically, we take the same climate model simulation and we tweak the initial conditions by just a real small round-off error, something like 10 to the minus ninth change in temperature. And we do that like 20 times, and then we run the simulation. And while all of these simulations will have the same amount of warming by the end of the 21st century, the differences between them due to this sort of random initial condition change is this natural variability. So really, we're trying to understand in this paper not only how different forcings like aerosol and carbon dioxide affect the climate, But we're also then trying to understand how does that differ from just natural variability?
I think everyone's heard of this. I don't know if it's a myth or a useful heuristic or whatever, but the concept that a butterfly flaps its wings somewhere on the other side of the planet, and that's the start of a chain of events that causes a tsunami. How much variability is there in the planet system with these small tweaks?
Yeah, that's an excellent analogy, and really where it comes from, how to set up these experiments by just tweaking the initial conditions. There's quite a bit of variability in the climate system. It can vary, as I said, on days, but it also has a variability from decades to multiple decades in time. It's quite large. I mean, if we take an area that is experiencing a lot of climate change like the Arctic, that's one of the areas that's warming faster than anywhere else on the planet. If you actually go back in the early 20th century, there was a relatively warm period in that Arctic, like not as warm as today, but warmer than 30 or 40 years ago. So it's this idea that there is a pretty large amount of natural variability, which is why it makes it difficult to really attribute climate change to different regions. So by running these types of ensembles, this makes it a lot easier to understand that range of that variability.
And let's get into some of the explainable AI sides of things. Obviously, when you have a complex system, it stands to reason you need a somewhat complex model to describe it. How can you balance that with the need to understand what the model's doing?
Yes, in this case, we're using very simple neural networks. The explainability technique we're using is this thing called layerwise relevance propagation. It essentially takes your features from your inputs and outputs. After you use this technique, it outputs a heat map telling you the relevance or how important that feature was to the final prediction from the neural network. So in every example our research group has been using, generally our neural networks are very simple, which allows this type of visualization technique to work really well. So we've been lucky that our inputs are quite data rich, and it seems that even though it's not very complex, our models, they seem to be still performing with high accuracy, but also they're able to be useful for these explainability techniques.
I have not had a ton of good luck in my personal life with heat maps. It seems like every time I make one, I essentially make a population heat map, even though I'm trying to make something else. When you have a climatologist eyes and you look at the layer-wise heat maps you're getting, what does it tell you?
I guess, going into this, the first thing I wanted to look at for these heat maps are, do the regions that pop out on the heat map, do they correspond to features in the climate system that I know are important? To me, that was sort of like this credibility check. The layer-wise relevance propagation method is really showing that the network is using real things in the climate system. So one thing that popped out in our maps is this really important area in the North Atlantic Ocean. And that popped out real bright on the heat map, suggesting that was a really important area for the neural network to learn to make its prediction. And in the climate system, I know that that area is very sensitive to these climate forcings. So to me, it was very much sort of checking with my eyes as a climate scientist with these heat maps to see what pops out to me as being important.
Thanks to our sponsor BB Edit from Bare Bones Software. If you're a Mac user and you have any need whatsoever for a text editor, which, let's face it, that's got to be all of us, you have got to check out BB Edit. BB Edit 14 provides Mac users the most powerful, professional-grade text editor around. It's known as capable and rock solid, and can process files that are large enough to bring other editors to their knees. This tool's been beloved for over 25 years, and I can understand why. If I'm just typing up some simple hello world, I guess any text editor will do. But when I really get into the weeds and need to do some data processing, maybe I've got a big messy file, I need to find all the non-ASCII characters and remove them, BB Edit's there for me. It has best-of-breed multi-file search and replace and great scripting support for text transformations. There's a whole menu of text transformations that you'll find handy. If you're a serious data scientist or software engineer, you're going to bump into situations where you need a powerful text editor. So download and try BB Edit today. You can get it at www.barebones.com. See how much your productivity can increase. barebones.com and download BB Edit. Today's data lives in the cloud, so your business needs a cloud-native, next-generation solution for intelligent, accessible data analytics. Astrato is a modern BI solution for modern BI teams. Your organization's data already lives in the cloud, which means you can access the single source of truth. Astrato accesses your data where it already lives with a live query approach, so there's no need for data movement, ever. You maintain the agility, speed, and elasticity that modern cloud data warehouses deliver. Astrato's gallery of examples will give you a quick impression of the power Astrato can give your team. The sales workbook example gives me a good indication of the quality of dashboard I can create for my collaborators. And the Tour de France workshop shows off a few other features on competitive cycling data that I could see being really inspiring on implementation for when I have a demanding executive that needs to really slice and dice the data in a lot of custom ways. When I first started exploring Astrato, I connected a Google Sheet of one of my datasets just so I could kick the tires. After that, integrating with Snowflake as a backend was super easy. You'll find that integration to be pretty painless and definitely worth your time checking out if you're a Snowflake user. With Astrato, you can bring complex data to life with no coding skills necessary. To learn more, visit astrato.io/dataskeptic. Astrato is ASTRATO, astrato.io/dataskeptic. And can you describe the underlying data set that you're training on? What is the input and where do you get it from?
So the inputs are coming from these climate model large ensembles. So we're taking these ensemble experiments that have these different forcings, differences in carbon dioxide, differences in aerosols, and then one other simulation that has everything that's supposedly realistic, just like the real world. And so my input to my neural network is actually just a map of temperature. I'm taking essentially an annual mean map, so one map for every year of temperature, going back from the historical period. So what I mean by that is like 1920 all the way to the future to 2080. So I essentially give the neural network this one map of temperature, and it's all latitude and longitude points on Earth. So it comes to something like 1,500 points or features that go into the network. And then this layerwise relevance propagation essentially outputs a heat map of those features which correspond identically to the map of latitude and longitude points.
When I think of machine learning, I'm always trying to make tabular data, but the Earth isn't quite tabular. It's an oblique spheroid. Do you face any challenges around quantifying the data because it's not in such a rectangular format?
Right. Yeah, that's a good question. It's definitely something our research group has been exploring. At least in the ways we've set up the problem so far, it almost seems that the neural network is learning to weight the importance of the different latitude and longitude regions to account for this spherical nature of the grid. So in our cases, we haven't really used any weighting methods for areas like in the Arctic, which have a smaller latitude and longitude grid box compared to the tropics. But I know for other types of groups which think about sort of weather prediction, they have definitely applied different types of weighting methods to give some latitude, some pixels more weight than others just because of the spherical nature. So I would say it's definitely a challenge and something I know a lot of research groups are thinking about how to take that into account for machine learning models.
So when studying these forced factors, you could run through a whole bunch of different examples of what if this was off by this much in this region and use these tools to get an understanding of how that might evolve. Do these layerwise maps, are they a sufficient answer then when you go and look at it, or are there other statistics you're considering as well?
For this paper, we're really focusing on, the patterns. So in our case, the heat maps actually correspond very nicely to these climate patterns that we're really trying to disentangle from the different forcings. So that's one of the main metrics. And as I've also mentioned, we set up our neural network very simply. So I don't think I've said, but the output of our neural network is the year of that map that I input. So it's essentially a very simple prediction problem coming at it from, I don't really care what year of the map it is. I care about more of the climate patterns. So in our case, the layerwise relevance propagation maps really reveal these patterns that we're interested in. How does the neural network learn that that map of temperature comes from that year? And then what does it look like between these different climate models with different forcings? So in our case, the visualization explainability part is really the heart of this work.
I'm not sure if I fully follow on predicting the year just yet. So I could definitely understand where the system could learn historically that, something was brewing in the Atlantic and it can see a later stage of that event. That could be something it could learn, I guess, a time series over years. But as you forecast these, aren't they drifting further and further from some ground truth timeline?
Absolutely. And so what we're really trying to understand is the climate aspect. So how do these forcings affect regional patterns in the Earth system through time? So essentially, can the neural network recognize these patterns that are attributable to the different forcings? So essentially, the neural network is learning this time evolving nature without giving it any information temporally to understand the patterns. Like, for instance, one area in the North Atlantic is actually cooling due to climate change, while the rest of the globe warms. So the neural network actually can identify this region, this anomalous cooling over the North Atlantic, to learn how it evolves in time, essentially predicting the year. And I think our group has used this idea of predicting the year for a couple different research applications. And I think going back to the initial, stage of setting up this problem, we were skeptical that it was going to even work, that the neural network how could it possibly learn, this temporal information by just being given this static map? And so I think what's come out of all of this work is that the layerwise relevance propagation is revealing these regions that temporally change. And the neural network is learning how these features correspond to each other and change through time.
You've described some of these neural networks as being simple. How simple are they? Can you describe the architecture a bit?
For these neural networks, we have 2 hidden layers, essentially 20 nodes in each hidden layer. And then this output layer is essentially predicting the year. So we've tried, different architectures, adding more complexity. And it still seems that about this complexity gives us the most accurate prediction for predicting the year of the maps.
And in thinking through the results and where this can go, obviously it answers a lot of scientific questions. Are there any policy questions we should learn about? Naturally, there's a lot that probably needs to be changed on that front, but as you've mentioned some of these hot spots or critical zones, do we really need to ban aerosols in certain locations?
Yeah, it's an interesting point. So one of these challenges, as I mentioned, for running climate models is this idea of these different forcings and how do we attribute changes in different regions to each forcing. And I think a result that came out of this work, and one we've known in climate science, is that aerosols are actually really difficult to simulate. They're really important for the climate system. So I think what comes out of this work from a climate perspective is that we really need to check how our climate models are simulating aerosols. Are they realistic with the real world, and how might it change going forward in the future? For instance, one thing we expect is that more and more aerosols will actually be cleaned up going forward in the future as more and more countries, add policies to reduce pollution. And so the question is, how are these changes in aerosols in the future going to affect overall climate change due to carbon dioxide? And I think these regions identified by this explainability method highlight some of the areas that could be particularly sensitive to changes in aerosols, and that we really need to check our climate models and see how well they're simulating this important component.
Do you have a sense of the degree to which the explainable aspects of this work, how critical does it hinge on that and getting things published?
I think that was definitely the critical part of this work, finding these regions and then comparing them for the different forcings. I think for me, at least in machine learning and how I feel about it with climate science, is that we need really these explainability methods or interpretability methods to really understand what's going on in these machine learning, black boxes per se. I think at least in our field, there's still some skepticism about these types of methods, but I think adding these visualization tools is so critical to getting more and more people thinking about trying other data science methods to understand important questions like climate change.
Well, I think a healthy amount of skepticism's good. I assume that when Einstein first published, physicists had to be initially skeptical. They've all gotten on board now. Where is the climatology community on the adoption of ML hype cycle?
I think it's growing exponentially. One thing I like to do every morning with my coffee is sort of go through the climate science journals and see what's being published and, what comes on archive or early online releases. And I think even just me in the last year, it's just been an incredible growth of applying machine learning methods to Earth system, Earth climate problems. And I think people are coming in from all different perspectives. To me, I've set up really simple problems, but used explainability methods to hopefully learn some new science. And other people are using it for prediction problems, trying to understand, weather forecasts. And then other people are using machine learning for parameterization. So how do we improve these climate models that I've been talking about? How do we improve their simulation of aerosols? And can we use machine learning methods to really reduce some of all of this computational demand to run supercomputers? And again, there's more and more growth in machine learning. And in fact, recently, one of our journals just came out with a new journal devoted to AI methods for weather and climate, which actually just came out a few weeks ago. And I think at least this society, it's called the American Meteorological Society, I really think by showing their adoption of this new journal shows how much growth is really undergoing for machine learning in our field.
And to what degree is it critical, or maybe not so critical, that someone with strong machine learning chops learn some fundamentals in climate science? Can I just come and brute force bring linear algebra to the table and help, or do I really need to know some of the underlying models?
I'm always a proponent of team science and transdisciplinary research. I think it's so beneficial to work with domain scientists and data scientists coming together to understand these problems. I would say, in my field, we are data rich. We have data coming from climate models. We have data coming from satellites, coming from weather stations on Earth. And all of these data sets come in different formats. They have different uncertainties, different grids. And I think someone who's outside the field, it's challenging to understand, especially the pre-processing stage of our data. And I think it's so beneficial to approach problems like climate change from this transdisciplinary idea, working together with domain scientists and data science to answer the questions, I think is really critical to understanding the data problems we have and potential solutions.
What are some of the open challenges in that regard? Is it compute or access to data or the volume? What really is a limiting factor?
I think all of the above. But I would say we have so much data right now and just almost not enough people to really analyze it. Our climate models produce, petabyte after petabyte of data, and we just really can't, using particularly traditional methods on our desktop computer, we just can't analyze all of this important data. So I think adding in, work with data scientists and using, non-traditional methods like machine learning, I think is really a way we're going to be able to really look at all of this data and think about it from different perspectives.
Well, climate's something that's very much on my mind. The more I learn about it, the more concerned I get. And I guess studying it for scientific reasons alone is more than enough to do good research. But I'm curious if you have any thoughts on the impact factor your work can have, if there's any direct correlates to how we make a positive impact in this area.
My work, how I think about it, is that I hope, I see climate science as moving a way that we're working with more and more people outside our small niche field. As you mentioned, climate is a huge problem. And I think more and more, I'm hoping that climate scientists work with people in other fields to think about our data and reach more impactful results. So I guess thinking about my current work as a postdoc, I see it in hope that I can show, we can use new tools to really understand the climate system going, in the past, present, and future. And by working with data scientists, we can really revolutionize our field by understanding all of this data we have.
Is this paper kind of the culmination of a line of research, or is this an ongoing effort?
For now, I've kind of moved in a slightly different direction, still applying, machine learning to climate problems. I think what I, envision this paper really is showing how we can use explainability methods to add credibility for machine learning. And I think by using these single forcing large ensembles was kind of a unique data set to really play around and show the value of something like layerwise relevance propagation. And I hope it sparks interest, in applying these types of methods to future machine learning problems. And I think there's an endless amount of problems we can think of setting up with machine learning. And I hope this paper shows that by adding these explainability methods, we can really learn new science.
The layerwise regression technique you applied is visually stunning. I'll encourage listeners to go look at the paper. Even if, like me, can't perfectly read the data without certain background, it's obvious that you can tell what the model's relying on and its specific features of the globe. So it works really well for this problem. I'm wondering if there are any other techniques you've explored along the lines of explainable AI.
Personally, I have not, because I'm still relatively new to machine learning, again, only a year into it. And for me, at least, this method is great because all of the data I work with always come in something like a map. And, what's awesome about this layerwise relevance propagation is we get a heat map of a physical map in return. And that allows me to really compare my data. So it's been great for a lot of the problems. But I'll mention, it's not a perfect method. It is subjective to how we interpret. I get one of these layerwise relevance maps even for wrong predictions. So sometimes it actually could be useful for understanding why the neural network was wrong. But I'll give an example from a current project I'm working with is essentially I use lots of different climate models and I input a map of temperature into the neural network. And then the neural network has to tell me which climate model produced that map. So we run many climate models because they're not all perfect. And in climate science, we then compare how well they do. And I was hoping then to input observations into this neural network. And then the output would be which climate model was most similar to the real world observations. And I would then use the layerwise relevance propagation to look at the regions that were most similar. But it turned out the interpretation of this layerwise relevance was actually the opposite of my intuition. Instead of the neural network using features that were most similar between the real world and the climate model, it actually used features that were strikingly different. So I will say, with these explainability methods, they're certainly not perfect, and there's definitely subjectivity that goes into them. And I'm hoping, moving forward in this sort of data science and climate science sphere to really explore different methods and how they compare against each other.
Well, I know in a lot of statistics literature, you always report a p-value, even though there's plenty of discussion about why that's not always the right thing. There's something to be reported in common cases. Do you envision techniques like yours becoming a standard in the published literature?
I think it's going to become standard to include explainability methods for machine learning going forward in climate science. I already can see it being used more and more. For a lot of us, who are not in the data science world directly, a lot of these methods are new. And even though they've existed in the computer science world, for up to a decade or more. So I think, as we discussed earlier, working between domain and data scientists will allow these explainability methods to be more and more common in climate science. And I envision in only a few years, more and more of these methods to be commonplace with any type of research publication that goes into my world of climate science, to have some sort of method to show how the machine learning model is making a prediction.
Well, Zach, is there anywhere people can follow you online?
I am on Twitter at ZLABE. And so in addition to research and thinking about these types of problems, I also am very interested in using data visualization to communicate climate change. So I'm very active on Twitter and showing different types of visualization methods to talk about climate change.
We'll have a link to that in the show notes. Zach, thank you so much for taking the time to come on Data Skeptic.
Great. Thank you for having me.
That concludes another installment of Data Skeptic Time Series. Thanks to our guest today, Zach Labe. Thanks to our sponsors, Bare Bones and Estrato. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.